even before we start this lecture, we start delving into this, I'm just going to show you this ice tray. Okay, so there are cubes of ice in it, and I'm showing this to you right now because I know by the time I get through half of this lecture, these ice pieces would have actually melted. But I'm not going to tell you why I'm showing you this. We'll come to that later. But for now, just see that there is ice. There is still ice in this ice tray. Now let's start looking at start going through the chapter. And the main idea here is we are going to look at all the domains in physics. We'll understand what it means to what all things do we study in physics. Again, like the previous section that we have discussed, this section might not be important from the exam point of view, not so many questions, but it will really help you develop interest in the physics. So physics basically deals with a lot of macroscopic things. Macroscopic things means large things, right? Normal things that we see in our daily life, the terrestrial things like cars, blocks, okay, this piece of ice, everything that we see in our daily lives. Also included in the macroscopic world are the planets, the star systems, the black holes that we see. All of those are also included in the macroscopic domain of the physics, and those come in the realm of classical physics. Classical means that those things have been studied for a long time. The first subdomain of the classical physics is mechanics, and of course this would be the major focus of our studies, and it is the most important portion. The mechanics, of course, one of the major things in mechanics is the Newton's laws of motion that we all know, but there are other things as well. So this is all that is covered in mechanics. Newton's laws of motion, typically what we will be dealing with, we will be applying to rigid bodies. What are rigid bodies? Rigid bodies are bodies which cannot really be compressed. Now the thing here is rigid bodies that we will be dealing with in our questions in these lectures, we'll assume them to be rigid. Ideally, no body is those are ideal conditions that the body is rigid. In real life, no body is actually rigid. Even you might say that this piece of remote, this remote that I have in hand is rigid. But actually, in reality, even this remote is not really rigid because I can compress it. If I apply some force to it, it will definitely bend. But to make things simple for us, and we'll understand that this is actually a very important principle of the study of physics, that we will simplify what we are actually studying, okay, so that we can focus on one thing at a time. And to simplify things, one of the basic assumptions that we will make is a lot of times that we will make is that the bodies are rigid. They are not really rigid in the real life. Understand that. Of course, rigid bodies, again, there are two kinds. One is statics. Statics means that things are not really moving. For example, everything that I have here, like the chair, the table, the screens, or everything, the screen that you are looking at, even those are static. Those are not really moving. I mean, you might be sitting in a car, and in that case, things around you might be moving, but the screen that you are looking at is hopefully not moving. Otherwise, we would be in trouble. And then there are things which are dynamic, and we study them intentionally when they are moving, right? For example, the study of cars, right? The crash tests, the cars, when they understand how safe a car is, they intentionally test it by moving it, okay? So those are the things which are studied in the dynamics. Then another thing that we will be studying, we will also be covering that, is deformation. What is deformation? Like I said, that no body, right? I mean, no object in this world is actually undeformable. They are all deformable. They are not really rigid. We can deform them if we apply pressure to them, and that would be the focus of our study. And then once the body is deformed, then we will understand if the body is deformed, then what kind of stresses develop when it is deformed. Does it try to come back, and would it gain its original shape? How much of it would remain permanently deformed? So all of those we will be studying. Then of course comes the study of fluids. Now fluids are completely different, right? Think about it, because fluids are always deformable, right? So they are an extreme case of if you think about it this way, deformable bodies, but there are separate laws which deal with them. And when fluids are flowing, then there are two kinds of flows. One flow is that the fluids, when they are flowing, they can be compressed or they can remain uncompressible. A lot of times we will assume that in ideal conditions the fluid flow is actually incompressible. And then of course, like anything else in physics, like I said before, we would simplify our assumptions just to make the calculations, we'll make simplifying assumptions just to make the calculations a little bit easier for us. If we just study the ideal things without any simplification, then the computations would become prohibitively expensive. With the help of computers, we can do that. But of course, in our studies, we will just study the behavior of bodies after making several simplifications. See, this is an example of a deformable body, right? This is a bridge, okay? And then we are trying to deform it. We are trying to apply pressure to it to deform it. So those are the things that we would be covering in mechanics. But remember that mechanics is just one aspect. There are other things also, right? For example, what is electrodynamics? Electrodynamics and electrostatics. So those are another two things that we would be dealing with. It's electrostatics and electrodynamics, right? So those are both things here, electrostatics as well as electrodynamics. What does it mean? So electrostatics means that when the charges are not really moving, they are just there, okay? Like for example, electrons are actually always moving, so we cannot really take their example. Let's say that, again, this is a simplifying assumption, right? So we'll just take a charge, we'll just put it here, and then we'll assume that it's not really moving. And then we'll understand what kind of interactions does this charge produce on other charged objects, which are not also moving. As we'll study, Coulomb's law is one of the laws which really applies here. Now, when charges are moving, things become a little, not really complicated, but they become interesting, I would say. When charges are moving, they produce not only electric field, they also produce magnetic field. And that is the thing about electrodynamics. So electrodynamics actually, like we also saw this in another class, and this is a simple motor, right? There is this magnet, and then there is this coil. And what happens is that if I rotate this coil in the magnetic field, then current is produced under certain circumstances. Okay, and then that is the study of electrodynamics, because as soon as I talk about current, it is the movement of charge. So that all of those things that have to deal with the conductors, currents, AC, DC, magnetic fields, those all come under electrodynamics. Now the next thing is, of course, optics. What does it mean by optics? Optics has anything to do with the lenses, the behavior of the how does the light diverge when it hits the lenses? What is reflection or refraction? All of those things come under optics, right? So this specs that I have right here would not really be there if there was no optics. So that is the next important branch of physics. Now the next thing that we will look at, the next important branch, is the thermodynamics. Now this is where our eyes would come in, right? So thermodynamics is very interesting. See, the thermodynamics does not deal with the motion of bodies. Now that comes under the domain of the mechanics. We already saw that. Forces, the motion, those come under the domain of mechanics. But what it deals with is that how do systems remain in equilibrium, right? And for example, if something is not really moving, then why does it not move? Or if something, for example, let's understand this ice, right? So this ice, like I told you before, now a lot of this ice has converted into water, right? Automatically, we say that spontaneously. It's just happening. I'm not doing anything here. I just kept ice here, and it is automatically happening. So this is this comes under the study of thermodynamics. So it deals with the energy of things. Like for example, if I have a gas in a container and I heat it, what would happen to it? Its pressure might increase, its temperature would increase. What happens if it's a closed container? What happens if it's an open container? All of those things are in the domain of thermodynamics. I mean, steam engine, if we talk about it, steam engine, our car engines in our cars and motorcycles, all of those things, right? When I'm burning something, the energy is produced. Now, how do I use that energy? When coal is burned in thermal power plants, when uranium is fissioned in the nuclear power plants, what happens there? How does the energy transformation takes place, and how do I increase the efficiency, right? For example, if I am burning this much amount of coal, I want to utilize all the energy and convert it into electricity. I don't want any energy to be wasted. That's my objective. Who would deal with these things? Who would try to increase the efficiency? Those would all come under the domain of thermodynamics, right? So there is one way in which we are converting the energy to work. The other way around also. For example, when the work is when we have electricity and the fan is moving, a part of it is electrostatics, electrodynamics. Then there is a second part also which will come under the domain of thermodynamics. Now when the refrigeration happens, when for example air conditioner, we have right here air conditioner, how does that happen? Why does it cool down, right? I mean, how does the air cool down? How do I increase the efficiency again? Those would come under the domain of thermodynamics. Then again, other things that we study in thermodynamics is, like I said, this particular reaction, it just spontaneously is happening, right? This is a physical change which is just happening. What is happening here? We are moving from ice to water. So the water molecules are spread out further, and this is a spontaneous change in something known as entropy. So this ice has less entropy, water has more entropy. What does it mean by entropy? So entropy actually means that I have more randomness. So water has more randomness than ice. I mean, we can envision that, right? Because water molecules are spread out further, so it has more randomness. We can sort of understand it intuitively that way. And again, this change happened spontaneously. The things which increase the entropy just happen automatically. And where does this result come from? It comes from thermodynamics. That if there is an increase in entropy, then that might happen spontaneously. So for example, the universe we know is growing. Why is it growing? Because there is increase in randomness. If the universe is expanding, the bodies are going far apart, and this would increase the randomness or entropy of the universe. And hence this change is spontaneous. It is just happening. Nobody is actually pulling the universe. It is just expanding on its own. So the same principle, increasing in the entropy, works here in the case of ice. It also works in the case of expansion of universe. And that's the beauty of physics. Like we said again and again, we will use the same laws and we will use it to explain everything in this universe. The same laws would apply everywhere. So that all of these things that we have discussed come under the domain of thermodynamics. I just explained it a little more because thermodynamics is something that we would not have touched in the lower classes, and you might be thinking that, oh, what are we going to do in thermodynamics? So thermodynamics deals with everything that has to do with heat and cooling and the entropy of bodies, of closed and open systems, right? Now, that is everything to do with the macroscopic world, right? So macroscopic world, we have touched that. There is another world which is the microscopic world. Microscopic world means that atoms, molecules, and even beyond atoms, we know that there are electrons, protons, neutrons, and even beyond those, we have further small particles inside them, which are known as quarks, right? And all of those things are in the realm of quantum mechanics. So all of those things, the theories related to them are dealt with in quantum mechanics. See, quantum mechanics is something that we will be touching on, but since we have not really studied many aspects of it, so we will not talk about it much here, but it is something that we will be going into detail, a little bit of detail. The last important aspect is something called mesoscopic. Mesoscopic means that it is macroscopic plus microscopic. It is in between these two things. And where does this come into play? This has become very important branch of physics of late with the advent of semiconductors. See, the thing is, with semiconductors, what we have done is that we have miniaturized things. We have just made things small. Now in a small phone, you have as much power as the big supercomputers used to have earlier. I mean, we all know that, we hear about it. But one of the things which has happened is that we have to miniaturize everything. We have to just make everything so much smaller. And once we make things small, what happens is that we have to deal with the behavior of things when they are only a few molecules, when they are only a few atoms large, atoms thick. And that is the mesoscopic world, where we are using the principles of both quantum mechanics as well as classical mechanics, and we are trying to solve the problem of a real physical problem, because we have to make things even smaller. Now I want the same cell phone, which is let's say this much in size. I want to make it this is smaller, and I want to embed it inside my wrist right here. I want to do that, but to make it, I'll have to make it even smaller, and that is why this mesoscopic things, they come into picture. I want to make nanoscale things. I want to make a nano machinery, small robots, which I can inject into my bloodstream and they can cure various ailments in my body. I want to do all of those things. But see, the beginning of all of those things would be actually physics. Once we understand the physics of few atoms, how they behave together, then I can really make those things. Without understanding, I cannot really make those things, and I'm not going to inject those in my body anyways, without really understanding them. So like I said, physics is the beginning of all technology, right? Some technological changes also force us to go inside the physics of those things. But of course, without understanding the physics, I cannot really create a successful technology. I'll have to deal with the physics one way or another. Now, this is the scope of physics. Like we already said that, and we have studied this aspect quite a bit, right? Where the speeds are less and the distances are larger than certain amount. So this is all under the realm of classical mechanics, where the Newton's laws actually hold. Beyond, if I increase the speed further, then I come under the realm of relativistic mechanics. Relativistic mechanics means that this is the mechanics which was given by Einstein. Now, if I decrease the size, then I come under the realm of quantum mechanics. So quantum mechanics is, like we said, is the mechanics of small, very small, tiny, even inside atom I am going there, then I have to deal with the quantum mechanics, atoms, molecules, and even beyond that if I am going. When the things are very small, as well as the speeds are very large, then we have a new domain, which is the quantum field theory, and this we will not be touching upon at all in our study. So we will be dealing with this, and we will be dealing with this, but we will not be touching upon the quantum field theory. So as you can see, the scope of physics is pretty large, is very, very large. It is, I think, very exciting time to study physics, to become a physicist, and not only to solve questions, but to really have interest in physics. See, now we know that physics has made tremendous progress, and of course that is reflected in our technological progress as well. I mean, without progress in physics, none of the technologies would really have happened. And what was the reason for that? Why does in the previous 2 centuries so much has been done in the physics? I mean, before 2 centuries, we didn't even understand basic things about things like atom. We didn't understand of things like electricity, about waves. We didn't know any of these things with certainty. And in the last few centuries, we have been able to just understand so much about the world and so much better. And what was this? What is the reason behind that? See, one of the most important reason is that we supplemented our qualitative thinking, right? So qualitative thinking means that there are philosophers who are doing things, who are understanding things, who are just thinking about things. So we supplemented our qualitative thinking with quantitative experiments. So we not only thought about things, we also started doing experiments. Now, why is that important? For some reason, for whatever reason, the world around us is actually it can be described very, very nicely in terms of mathematics. For some reason, we don't really know why does the mathematics describe our world so well. Why does the Newton's law of gravitation hold? Why does the mathematical description, right? So we know that Newton's law of gravitation is actually described as force is equal to G m1 m2, where m1 m2 are the masses upon r square. So we know that this is the Newton's law of gravitation. We know that. But why does it actually hold? Why is mathematics able to describe it at all? Right? I mean, it could have been anything, any random thing, and it didn't really have to change as r square. It could have been r raised to power 1.5, and that would have made our things very, very difficult for us. But for whatever reason, it turned out that mathematics was able to describe our world very nicely, and for some reason, even the most complicated things, when they were condensed in terms of mathematics, the equations came out to be surprisingly simple. For example, the entire electromagnetism, the entire theory of light, electricity, and magnetism can be condensed to 4 equations, just 4 equations. Those are the 4 Maxwell's equations. Okay, and if you go into the physics of this a little bit more, if you go into higher level of understanding of mathematics, then some people say that it can even be condensed to just 1 equation. So now that is the beauty of the mathematics, that using mathematics we are able to describe the physical processes very succinctly, very smoothly, and it gives us a great power. Why does it give us great power? Because we are able to now predict things. I can put things in the formula. For example, as soon as I have this formula of Newton's law of gravitation, as soon as I have it, I can not only determine the gravitational attraction between the earth and moon, I can also describe the gravitational attraction, the gravitational force between these two bodies, right? So those things I am able to do. Why? Because I have this powerful formula. That is the first thing. The second thing is we have universality. So one of the things that we have done over the last few centuries is that we have created universal laws. So the universal law of gravitation, that's what we call it, Newton's law of gravitation, right? Because it applies universally to all the objects. Similarly, Einstein's theories, those apply to all the objects. We all also look at the Newton's laws of motions. Those are also fairly applicable. Similarly, quantum theories, those are also fairly applicable to vast majority of objects. So those, as soon as we have a law which applies everywhere, then I can use that law as the basis and develop more laws on top of it. And if there are a lot of exceptions to these laws, then I'll have to think, well, whether I can apply this law here, whether I can assume it will be true or not. But that is not the case. For some reason, these laws, they apply fairly widely. And because they apply fairly widely, I'm able to use those laws. I'm able to build on top of those. The other thing is that we have been able to approximate very well. Now, what does it mean by approximation? This is what we touched upon a little bit earlier in this lecture. What it actually means is that I am able to understand the things in isolation. Like for example, let's just take this simple example. I have a feather and I have a stone. Now you know that if I drop these two, the law of gravitation actually tells me what would happen. We already know that, right? We already know that if I drop this stone and this feather down, then they will go down, and if there was no air here, then they would actually go down and touch the floor at the same time. Of course, that does not really, it's not something that we actually observe, because air is all around us, otherwise we would not be here alive to do this experiment. And if I drop this feather, it will come down slowly. That's what we would observe. And if I were to drop the stone, it would come very, very fast. That is because of the air drag. Now, when we understand the law of gravitation, we just assume that there is no air drag. So we have created a simplified system just for our study. And using that simplified system, I can extract the essential aspect of law of gravitation. So that is what it means by approximation. We will do this all the time, right? We'll do this all the time in the case of physics. We'll just make things simple for us so that we can focus on one thing at a time and not just delve into all the things together. Now, with this, we come to the a little bit sort of philosophical things here. There are three things that you should understand. One is hypothesis, second is axiom, and the third is model. Now, what is the difference between these three? See, if you have listened to the earlier lecture, we talked about the scientific process. So, scientific process means that I assume something, and then I look at something, I create an hypothesis. What does it mean by creating a hypothesis? I assume that I predict that this is why something is happening. For example, the sun rises every day. So one fine morning, I will just create an hypothesis. So it is rising every day because the earth is moving around the sun. Or I could assume the other way around also, the sun is moving around the earth. Of course, those two bodies have to be in relative motion for us to see the sun move in the from one side, from the east to the west. For us to see the sun moving across the sky, the earth and the sun have to be in relative motion, right? So it has to be one of those two things. Either, or it could be both. It could have been that both sun and earth are moving. Okay, but of course, that is indeed the case. We now know that both sun and earth are moving, but when I'm talking about movement here, it is relative to each other. So relative to each other, sun and earth have to be in movement. So I can create, like I said, several hypotheses to explain this effect that the sun rises every morning. There are 1,000 hypotheses you can create just to explain this one effect. So that is hypothesis. Hypothesis is something that I think explains why an observation is being observed. Okay, so this is just a hypothesis. It does not say whether my hypothesis is true or false. You can create as many hypotheses about an observation as you want. It does not mean that any of that is true. This process of actually creating hypotheses and testing them for validation, whether they are true or not, we are doing in our life every day. We are doing it all the time without even knowing. Okay, so that is the hypothesis. Okay, so now what we then say is axiom. Right? The second thing that we are understanding here is axiom. What is axiom? Axiom is the self-evident truth. In any theory that we create, we assume that certain axioms are true. For example, when Einstein created the theory of relativity, he said that the speed of light is invariable. Okay, that is what we assume now. In speed of light in vacuum is always constant. It comes out to be the same whether I measure it here, whether I measure it across the universe, wherever, and no matter what the time is. Even if I change the time, this speed of light would not really change. It has been the same from the beginning of the universe, and it will remain the same until the universe ends. That is the assumption. Okay, we cannot really see that if it is going to be true all the time. Okay, whatever we have observed so far, okay, matches that assumption. So it's an axiom. Okay, and whatever we have observed so far, whatever experiments we have done, we have never seen that our axiom that speed of light is constant has actually changed. Okay, but it is not something that we can really prove. Now that is the most important thing. An axiom is just self-evident truth. It is an accepted truth. We just accept it to be true. It cannot be tested, but based on these axioms we can create further results. So Euclid, again, when he created his geometry, then he assumed that the parallel lines would never meet. Okay, so that was the axiom that he just assumed, and based on that axiom he created rest of this geometry. Now you might assume something else and create your own geometry. Okay, so your axioms would be different than his. Okay, and the main thing here is that neither his axioms should be, if his axioms have been disproven for whatever reason, if he now understood that the parallel lines actually met, then his entire geometry would be wrong. That is the most important thing. If for some reason we found in some experiment that the speed of light is not really same, it changes in vacuum depending upon some other thing, then our entire physics is gone, because we have just assumed this axiom when we have created anything in physics. The third thing is model. Now what is model? See, the model actually means that we explain the results of our experiment by creating a model of something in our minds or on paper and just publishing it all over. Okay, and that becomes the, if it's accepted by the scientific community, that becomes the norm, and other people also assume that model, and based on those models then they conduct more experiment, either to validate it, or they might conduct experiment whether this model is valid or not. They might test it, our model, or they would assume the model is true and then go on further with their experiment. So model is a theory which is proposed to explain a phenomena. We know that Rutherford created his model of atoms. So that is another class that we have taken. You should definitely watch it. Rutherford created his own model of an atom to explain his gold foil, the results that he saw in his gold foil experiments. So model is just a mental picture of how something is. This is how an atom should be, and I'm not really seen an atom. I cannot really see it. I cannot really observe it. But based on the experiments that I have done and the results I am getting, this has to be the case, that an atom should have a very dense nucleus. This is what the Rutherford said. So that is the next important thing, a model. So those are the three things that you have to understand. Each of these three things has its own importance. Of course, we will not be solving numericals based on this, but these three hypothesis, axiom and model are important. You have to understand, you should understand the difference between these. Thank you.